everyone. Thanks for being here and thanks for the introduction. As Professor Prats introduced me, the main focus of my research is doing climate optimal trajectory planning at the network scale. Today I'm going to present our latest study, which is focusing on climate hotspot avoidance, considering the complexity of the traffic using constrained multi-agent reinforcement learning. So we missed the first slide, so you couldn't see the title. But let's go for the introduction and the motivation. Okay, done. Oh no. But then, yeah. As you heard during this conference, maybe hundreds of times, aviation is one of the contributors to global warming. Actually, it is responsible for 3 to 5% of the human-induced climate change. And it contributes to global warming through the emission of CO2 and non-CO2. Different strategy has been proposed to mitigate the climate impact of aviation. Most of them are mainly focused on the CO2 effects, such as, for example, alternative fuel or technological advancement. They can also be beneficial to reduce the non-CO2 climate effect. However, they are medium to long-term measures. So as we move toward this advanced strategy, we need to find some short-term also measures. On the other hand, non-CO2 effects has been claimed to be 2 times higher, their effect 2 times higher than CO2, though with high uncertainty. And they are highly depend on the time and location of the emission. So we can find climate optimal trajectories which avoid sensitive areas to the aircraft emission to reduce the total climate effect. They are feasible with existing infrastructure and they are relatively immediate solution. So many researchers has explored the potential of using trajectory planning to reduce the climate effect. But the question is that to what extent these trajectories are feasible, because they are focusing on single trajectory optimization, but they do not look at their network effect. Is this trajectory really feasible? And what are the challenges to adopt this trajectory at the air traffic network scale? Here you can see a comparison between 2 different sets of trajectory. The first is business as usual flight, and this is climate optimal flights. The light areas here shows the climate sensitive areas, which climate optimal trajectory try to avoid this area. As the result of this avoidance, we redistribute the traffic flow, and in particular area, for example here or here, we increase the congestion, and as the result, we increase the complexity of the traffic. So we need to find a way to balance these 2 objectives. It means that we should find trajectories which are feasible from the ATM perspective at the same time that we are looking at their climate effect. We have a table for the latest study on climate optimized flight planning. We classified it based on 4 different features. Their scale, if they consider the performance at the ATM system, if they propose any resolution to compensate for the negative impact of the optimized trajectory, and the aerospace that they consider. If we exclude the last, which is our work, our previous work, you can see that most of them perform trajectory optimization at single step. It means that they just find the optimal trajectory for a single flight without considering any ATM performance metric. They obviously did not propose any resolution method, and most of them actually was performed at the free routing aerospace. But we need to see this problem at the larger scale. It means that we need to consider the climate impact, we need to also consider the air traffic manageability, and we also need automated framework, advanced framework that can be used in fast time with high performance. So the intersection of these three objectives has been identified as an open gap, which in this study we are going to address this. Based on this identified gap, the research objective in this study is to mitigate the climate effect, consider maintain the manageability of the air traffic system, and propose an automated and efficient framework to find a solution. When I started my PhD, actually, we came up with this idea to do a kind of multi-step optimization. This way, we first get as input weather data, traffic scenario, and route network. We optimize each individual trajectories. After having all this trajectory, we integrate them into network scale and assess their performance in terms of demand, the number of conflict, or the complexity of the traffic. And then we propose a resolution strategy to find some modifications to the optimal trajectory to kind of compensate for their negative impacts. However, we faced some limitations with this approach, like micro-scale trajectory optimization is time-consuming. We need to optimize all individual trajectories separately. And then this adjustment in this part for the resolution further increase the complexity. And the adjustment here in the resolution may reduce the optimal performance, which we achieved at the trajectory level. And we do not have a feedback mechanism here between the resolution and the climate optimality. So we thought that instead of having this multi-step optimization, why not having a kind of more efficient framework and propose a deep adaptive model with fast execution time. This model should be able to get as input business as usual trajectory, planned trajectory before, and as the output, we will have feasible climate optimal trajectories. Inside this model, we mitigate the non-CO2 climate impact and we maintain the manageability of the ATM system. How we do it? We model the problem as a constraint optimization. We identify areas of the airspace which aircraft emission has high impact in terms of warming, and we call them hotspot area, and we modify flight trajectories to avoid this area. So we can see this as a constraint and add it to the optimization. And as the objective, we can consider the complexity of the air traffic and try to minimize it. And then, to solve this constraint optimization problem, we can use conventional multi-agent control approaches. However, they are not very efficient. They have some limitations in terms of dimension of the problem. We will face the curse of dimensionality because the state space and the action or control space will grow with the number of aircraft in the airspace, and it's exploding. And aircraft dynamical models are highly nonlinear, and it is a kind of large-scale coupled optimization because each aircraft is trying to minimize the complexity, but the complexity is shared between all aircraft. So they need to consider, for example, if one flight should consider all other flights to reduce the complexity. And it is scenario-specific solution. What does it mean? It means that we optimize the traffic for today, but it's not a solution for tomorrow. So we need to redo all this for tomorrow and every day. But multi-agent reinforcement learning has been appeared in recent years, and it shows great promise to solve complex problems. It can address some challenges in the multi-agent control approach. For example, for the case of dimensionality, multi-agent reinforcement learning can generalize using function approximations such as neural networks, and it can work with model-free dynamic, so it doesn't need a specific dynamic of the aircraft. It's just a kind of trial and error and doesn't need the specific dynamic. And we can also design the reward function of the agent to be kind of to implicitly consider the objective of our agent. And it is adaptable, meaning that if we train a model, we can use it for another scenario. For example, we can train with the data of like particular month or day, and then use it afterward for another scenario. So we don't need to redo the simulation each time. But how can we use this framework? To solve this problem in the framework of multi-agent reinforcement learning, we model the problem as a partially observable constraint Markov decision process. We can show this Markov decision process by this tuple that you can hear. And it consists of the number of aircraft in the aerospace. It has the A shows the action space that aircraft can select. O is the observation space that the agent receives. R is the reward function, and C is the cost of constraint violation. We also can have threshold value for the violation and apply it. This way, at each time step T, each agent receives the observation from the environment. They take action according to a defined policy, and the joint action of all agents are applied to the environment, and a feedback will be provided for each agent, which the feedback shows that the reward that they achieved and the cost of violation. So the goal is to find the optimal policy for each agent, which maximizes the reward while satisfying some constraints. In very large-scale problems, finding this policy is not very easy, so we can approximate it using neural networks, and we then call it deep reinforcement learning. So with this setting, instead of looking for the policy, we look for the parameter of the policy. Here, to continue the formulation of the problem, I will present some assumptions and some definitions. The assumption is that it is fully cooperative setting, meaning that they have the same reward, like the complexity of the air traffic will be calculated and shared with all aircraft. And then they are homogeneous agents, meaning that they have the same reward function, same observation space, same action space, and and same action space, and they have the same capability in the environment. So just to clarify, when we say that they have the same action space, it means that the action that they can select is a specified like sets of action, but they can select different action. It's not exactly the same action that all take. We have some definitions here. We define the reward value function, which is the value of each state or the expected reward at each state. And the Q is the state action value function, which shows the expected reward being at a specific state and doing a specific action. Why we do that? It's because we have the reward, but we do not have a kind of function which we can do the gradient or this kind of thing. So we define these functions and we estimate them using neural networks. And we also have advantageous function, which is like the advantages of taking a specific action at a specific state relative to the baseline. So the objective is then formulated to maximize the reward value function subject to some constraint. It's the same, just the definition are changed to continue with the formulation. We can use adaptive Lagrangian multipliers to add the constraint in the objective function. And then this Lagrangian multiplier is found iteratively during the training. So it is not fixed, so we do not have a specific challenge to find. And then we use the framework of proximal policy optimization, which is a trust region policy optimization. We define a surrogate objective instead of objective function, which has a kind of clipping mechanism here, which it clipped the probability ratio between the new policy and the old policy within a specific range to ensure that the new policy remains close to the old policy. So we do not have huge difference between two policies, and it avoids instability in the training. And the advantageous function, as I already mentioned, is the advantage or the benefit of taking an action relative to the baseline action. And we iteratively find the parameters of the policy, theta, and the lambda, which is the Lagrangian multiplier. So, to solve this problem, we need to still define what is the observation space, what is the action space, and the rest. This is the framework that we proposed. Here, as I already mentioned, each aircraft, the policy is estimated with a neural network, and then each of them receive an observation. They take action. This action goes to the environment. We do the trajectory prediction. Like, we receive the new action, so we need to redo or recalculate the trajectories. We also have a reward function to calculate the complexity of the traffic with respect to the new trajectories and the cost of violation. And we also have observation module to find the observation for the next step. All this information are stored in a replay buffer and used to train these networks, which these are policy and these are the value function. And it will be repeated until we find the optimal policy or we see a good convergence. In this problem, the observation space consists of two main parts. The first is trajectory and hotspot information. The trajectory includes the latitude, longitude, and altitude of the aircraft during the time step that we want to perform the action. And the hotspots area, the information of the hotspot consists of the location of each hotspot, the center of hotspot. And we also need the information of the neighboring aircraft, because in the end we need to reduce the complexity, and the complexity is depend on the neighboring aircraft. As the action space, we are allowed to increase the Mach number by 0.03, maintain the current Mach number, and reduce it. Also, we can increase the flight level by 20 hectofeet, maintain the current flight level, or reduce it by 20 hectofeet. The reward function here is the difference between the initial complexity, meaning that the complexity of business as usual trajectory, and the complexity of the new trajectories. So if we have the same complexity as the initial trajectory, the reward would be 0, then the agent receives nothing. If it is larger, the agent receives a negative reward, which is not good. And if it is lower, so the agent receives a positive reward, it knows that it will learn that this action was kind of useful, so they should increase the weight of that policy. Okay, this was the framework. So we did an analysis on the aerospace, on the economic aerospace. The trajectory used are on December 20th of December 2018. It is from 12 to 4 in the afternoon. And the weather data, we used aerofoil reanalysis data. And the initial trajectory obtained using the in-house our in-house tool called Roost. It is, this library was developed as a part of my colleague PhD, and it is good and efficient to plan trajectory at structured aerospace. We can also use the trajectory of DDR2. I mean, we just need initial trajectory. It doesn't matter which kind of trajectory we have. We can treat them all the same. And about the hotspot, we considered fictitious climate hotspots. We generate hotspot ranging from FL 280 to 420 with 75% probability of occurring. The location is random and their shape are ellipsoids. So this is the climate hotspot violation of the initial trajectories. The red areas show that if we cross a hotspot, so like for example this part, it shows that many trajectories violated this hotspot, and also here. But when we apply our algorithm, you can see that we successfully managed to avoid a high number of hotspots. For example, here or there. We could find a way to avoid these hotspot areas. And when we look at the complexity of this set, you can see that this is the complexity map of the initial trajectory. And when we applied our proposed algorithm, the complexity map would be this map. Which, if you compare it, we can see that almost like we kept the range of the complexity in the same order, although in some areas, for example here or here, we reduced even the complexity. But it's important to note that if we want to reduce the climate effect, as long as we can keep the complexity of the traffic the same as before, the initial, it's good. We didn't compromise the traffic performance, but we achieved climate benefit. So, but here we also achieved some benefit in terms of complexity of the traffic. Further, we 2 minutes, okay? Maybe I just don't need to. It was the same analysis. So, as the conclusion, actually, we realized that we can mitigate the climate impact of aviation by trajectory planning, but it comes at a cost of reducing the manageability of the traffic. So we need a mechanism to consider the climate optimal trajectory at the network scale and assess their performance in terms of the complexity, demand, or whatever. And in this work, we proposed a unified method framework that we can do so, and it showed promise to be used for planning climate optimal trajectory at the network level. Although there are some discussion and definitely some limitations about this study, the main limitation is that we consider fictitious hotspot, but we can use a real hotspot seamlessly and incorporate it in the objective function. So we can use ACCF or COSIP to identify hotspot and model them as ellipsoids. And then the aerospace user preferences such as fuel consumption and flight time have not been considered in this study, although the initial trajectory were cost optimal and we did just some modification. So it was kind of indirectly applied. But we can also directly consider this increase and add another constraint. And finally, the lateral path was excluded from this research, and we did only a speed modification and flight level modification. But for future, we need also to add the lateral path modification, and we can also consider other ATM performance. For example, we can consider workload or demand or whatever you are interested. Thank you so much for your attention, and sorry for the